wrap that up good. So hopefully we got YouTube uploads figured out too. I think all the goofiness with uploads I think has been taken care of. I was clogging the bandwidth for a while at COCC, but now I just upload at night when nobody's around, which seems to work. Plus I downgraded the video quality a little bit, which I know will make my hair look a little less fantastic, but I think you guys can live with that. Please.
So normally it'll be up the day after?
I try to. I think I'm back on a 24-hour cycle now, Jack, absolutely. So I think I'm getting to the point where I'll record today, I'll dump it to the computer tonight and start uploading, and then hopefully tomorrow they'll be ready to go. At least that worked for yesterday. We'll see if I can keep that path going. There are some issues with this camera that haven't worked out yet. Like you can't delete from it. You plug it into the computer and it opens up as a file. I actually had to call tech support yesterday on that, or over the weekend on that. And while the guy had me on hold, I figured the problem out. When he came back, he's like, I haven't solved your problem. And I told him, well, I have. So why don't you record me explaining it to you? And that way when somebody else calls you, you can play my voice back. And I'll take out your paycheck. Love that. He didn't get for that too much. So I don't know. But anyway, I can't delete from it. So it's a little bit more, there's a couple of things like that. It doesn't recognize it as a hard drive, all kinds of goofy garbage. So if anybody's in the market for a video camera, realize there's some interesting stuff, like there's no on button. And this is coming from a guy who used to use the ones that sat on your shoulder with the big tape that went into them. So this was definitely a wake-up call for me. A video camera fits in my old digital camera's pouch with room to spare, a banana or two in there. So it's a new world for me, but there's some interesting stuff. Like there's hardly any buttons on the damn thing. I want buttons. I'm a button guy. I was born in '73. I want buttons. But anyway, we got that. What the hell were we doing yesterday? Last week, last Thursday. What were we doing? What were we doing when we stopped? Don't remember anything. That's okay. Go watch the videos. What were we? We were spinning pennies. We were spinning pennies. We sure were. Why were we spinning pennies? Just to waste your time? What was the point of spinning the pennies? Good. Give me some more. This is Lindsay, right? No, this is not Lindsay. This is Lindsay. This is not Lindsay. This is Dan. You're Lindsay. Don't do that to me, man. Second week of term. I'm trying to learn names. Lindsay, why? Anybody? I hear the word margin of error. I love that. I love that. What did we decide? Well, first of all, why did we spin the pennies in the first place? What were we trying to discover? What was the question that we answered? I had it written on that board. You might not remember it. It's okay. I didn't write much that day.
What is the probability of penny lands heads up after spinning twice?
Fantastic, Lindsay. What is the chance that we get heads on a penny after spinning? And allowing it to fall over on its own power. Very nice. Thank you, my friend. Perfect. What was our initial guess? If, without doing an experiment, based on our prior knowledge of what we know about coins and what we do with coins, besides purchase soft drinks and snacks with them, what was our initial guess?
I don't remember, but I'm guessing 50.
Yeah, that's exactly what it is. 50, tell me your name again.
Eric.
Eric, thank you. You don't have to remember, because we all said 50-50 immediately. We said 50-50 immediately, because that's what we're used to. We're used to flipping a coin, catching it, putting it on our hand, and having heads and tails be equally likely outcomes. Perfect, absolutely perfect. Now, what did we decide based on our data? If you remember, we spun, if I remember correctly, and I just looked at that, we spun 260 coins, or I should say we spun 26 coins 10 times each. So 260 spins. And how many heads did we get? You remember? This has never happened before in the history of me doing this experiment. How many heads did we get?
130.
We got exactly, and tell me your name again. Acacia, thank you. We got exactly 130 heads. We got exactly 130 heads. Exactly 50-50. That has never happened in the history of doing this experiment. I'm going to show you the history here momentarily. Okay? So from this, I want to talk a little bit about some symbols that are used. That thing's recording, right, Jesse? You see the REC button out there, you guys? It's going. Okay, good. There's a few symbols that I want to kind of bring in. Margin of error is a big one. But we're going to talk quickly about what we get from these two numbers right here. 260 coins. That means we did 260 trials. And we're going to carry that back from 243 and call that n equals 260. Just to have a nice variable we're used to from back in the day. And then we kept track of how many heads we got. We're going to call that x. And again, this, if you will, calls back from 243 as well. Although in my class we didn't talk variables too much with the binomial, we just kind of called them we kept track of trials. Successes were dealt with in a t-table, in a distribution table. But if you think about a distribution table, and you've got the outcomes on the left side and the probabilities on the right side, we called the left side x. That was x equals number of whatever, whether it's number of girls in a flock of chickens, whether it's number of broken legs at Mount Ashland on a downhill mountain bike trail, whatever it is. X is what you're interested in, and this is what we're interested in, the number of heads. So we got x equals 130. Perfect. Perfect, perfect, perfect. There was a somewhat new symbol we talked about early in class last time. And I made a joke about the nurses used to laugh whenever I mentioned this one. Remember what that was? The little p with a hat on it. That's what made it so funny. The p hat. Right, little p, very, very good actually. Thank you, Lindsay. Because big P means something very, very different in this course, which we'll get into next week. And unfortunately, your TI does not differentiate between little p's and big P's. That is a problem with a capital big P problem. Because there are like 5 or 6 different P's in statistics, and they all mean something different, and usually not interchangeable. So we'll differentiate all of those. So little p with a hat on it, we just call that guy p hat. What is he? Remember what he is?
Is that a sample proportion?
Oh, Eric, perfect. It's a sample proportion. It's a sample proportion. And it's a sample proportion of whatever you're studying. Do you notice how we use a little p up here to stand, as Lindsay said, for probability? It's the same. That implies the same thing. Probability, probability. It's just that this p without a hat implies the probability where?
Population.
Thank you, Will. In the general population is where that guy implies. So p hat is the glimpse we get into that general population by doing a sample. Does that kind of make sense? Do you know what this is in the population? That's the problem. You're never going to know what that is unless you get every penny on earth and spin it infinitely many times and keep track for infinite trials, which you can't do. So you draw a sample and you take a look at that. That's the whole point. So p hat computationally is very, very simple. Computationally, it's just x over n. And that hopefully rings a bell. In 243, generally you didn't have to create these, they were given to you. I would say something like 85% of Americans are insured, or 8% of Americans approve of Congress, the job Congress is doing, or something like that. And that number was given to you via a study that was done. But we didn't do the studies in 243 too much, because that's what 244 is about, is actually collecting the data and seeing what happens. So for us, for our data here, our p hat was the 130 over 260, or exactly 1/2. So we're done, right? Because I asked the question, what is the probability that we get heads after spinning? And we just answered that question, didn't we? It's 0.5. And we're done. We put our markers down, and we go get a latte, maybe a biscotti, late breakfast, on our next class. To which Acacia says, "To hell with you, Rule, we're not done yet." Why would she say that, other than the fact that she's drinking a bottle of water and I shouldn't have called her name because I'm bitter? Why should we not say we're done? Why are we not done by calling it 0.5? Why do we need a margin of error, Lindsay, or anyone? We need to apply a margin of error to that. Why? And if we didn't test, very nice, it's a sample, we didn't test the whole population, so why do we need a margin of error? These two reasons are extraordinarily overreaching reasons. What could happen if we run the experiment again?
It might not be exactly 50-50.
It might not be exactly 50-50. It might vary widely from 50-50, or it might be very, very close to 50-50. So we have to apply a margin of error to that 0.5. Remember what it was for our case? We used technology very quickly to get this, and we're going to go back and look at that again today. Remember what the margin of error was on this bad boy?
It was like plus or minus 0.06.
That's 0.06. There it was. Plus or minus 0.06, which stands for 6%. Just like 0.5 is 50%. So that's one way to write what's called, and I'm going to come back and define a few more terms here in a second that we're going to use over and over again in this course. But this is one way of expressing that probability. It's 50% plus or minus 6%. That's a totally valid way of doing it. That's a Gallup poll way of doing it. If you look at a poll, Rasmussen poll, Quinnipiac poll, Gallup poll, CNN poll, Time poll, whatever, Fox News poll, you're going to have the proportion up in the main area of the display, and then underneath you'll see margin of error or sampling error or some term like that, and it'll say plus or minus whatever %. And that's one way of doing it. Sometimes an easier way, and I say sometimes because this might not be easier for some folks, is writing it like this. 0.4, what would that be, 44 up to 0.56. That's another way of writing it. That simply takes, the 6% and adds and subtracts it to the estimate of 0.5, and then it gives you this range of values. That range of values is what we're going to spend some time today talking about. Because that range of values is the key. That's the key to everything. And I want to come back to our historical data. Any questions thus far? That's about as far as we got last time, I think. But any questions? Oops. Thus far?
I don't want to take us backwards, but remind me how we got.
No, go, Will, go, please.
0.06.
It was magic on Thursday. We ran it through the machine. And that's what I want to get into today is where the magic is not magic. And I apologize. One of the things I was supposed to record on Friday was a derivation of the formula for margin of error, which I will do this Friday, I promise you, and I'll have linked for you on your new camera. But I didn't get to it Friday. I was really very, very peeved about that actually, because it was, and I promised you in class, I'm like, don't worry about this. You'll have a justification for it tomorrow. I was a liar. This damn camera wouldn't agree with me, but that's okay. We'll get it to you, I promise. All right, let me pause this real quick. I discovered that